Okay. Yeah, it's a great pleasure to be here at this exciting workshop, which promises to be an exciting workshop. And being here is a particular resonance for me because I was a young postdoc here in Minnesota from 1992 to 1994, so older than a good fraction of the people in the audience. At that time, it was called the Theoretical Physics Institute, and which then morphed into the Fine Theoretical Physics Institute. And that was a particularly exciting time because with the fall of the Soviet Union, we had this influx of really outstanding physicists there to Minnesota. We had giants like Arkady Weinstein, who was sitting in the audience, Schiffman and Voloshin, here at that time. So, and we had people like Gribov coming through. And so it was extremely exciting to kind of watch these somewhat intimidating people and kind of learn from them. So, and also several of the ideas that I'm going to talk about actually were developed here in collaboration with Larry McLaren, who was then director of the Institute, and then subsequently also by him and other collaborators as well. And so this really is a testament to his impact on some of the things I'm going to talk about. So, anyway, so what I'm going to talk about, as I mentioned, is in my title is weak partons. And so why do they matter? So here's the kind of space-time diagram of a high-energy hadron collision. And so what happens is the sort of hard partons, which carry a large fraction of the momentum of the hadron, they essentially go through in the collision. This is sometimes called a leading particle effect. And so they sort of go propagate along the light cones, as shown by these blue these things in blue here, while the weak partons, which are the soft partons carrying small fractions of the momentum of the hadron, they kind of populate this central region, and they're numerous. And they lead to multi-particle production, as illustrated by this iconic image from the Stark detector at the relativistic heavy ion collider at Brookhaven. So, so in terms of rapidity, so you can think about this in terms of the space-time rapidity, which is roughly the momentum space rapidity. It's actually identical for massless particles. And so central rapidities correspond to this region here. And so this goes from, say, plus infinity to minus infinity in rapidity. So I'm going to be talking a lot about sort of the rapidity evolution of some of this physics. So how do we think about this in QCD? So this is a picture that one can keep in one's mind, which is if you imagine the hadron at large energies corresponding to these constituent quarks, which carry the quantum numbers of the proton, which are then dressed by these soft gluon clouds. And now imagine that it's boosted to very high energy. So these objects get time dilated, so they live longer and longer. And say you were to resolve this with some probe on some very short time scale, which has some resolution q squared, then as you go to higher and higher energies, you're going to see more and more of these weak partons. So you're going to see configurations into which the proton fluctuates, Fock states containing large numbers of these weak partons. And that's precisely what is shown to you by this picture here. So this is the parton distributions as a function of this momentum fraction x. So as you go to smaller x or higher energies, at, say, some fixed resolution scale, you see more and more of these weak gluons, which are then accompanied by their quark-antiquark partners. These are the C quarks. So that's sort of alpha s over pi sort of suppressed, and you see that's what you see is what you get. So these are sort of these weak partons in the collision are released as Bremsstrahlung. So you can ask, well, how is it? I mean, aren't they just suppressed by the coupling to see more and more of these weak partons? And the answer is that the coupling is compensated by the large phase space for Bremsstrahlung of these weak partons. So as you go to smaller and smaller x, this factor that appears in cross sections is of order 1, and so you can get so you have to sort of resum this to all orders, And that gives you actually a Markovian growth. So at each say rung in emission in rapidity, the rate of emission is proportional to the number of partons there. That's a Markovian process, which is an exponential growth in rapidity or a power law in x. And so that explains this very rapid growth in the cross section. So as you go to say x is a 10 to the minus 4, the proton is completely dominated by gluons and C quarks, with the valence degrees of freedom falling off very rapidly. So if you ask now, well, okay, what is the space-time picture that this corresponds to? Where do these weak partons actually sit? And how do we understand this in terms of the intrinsic sort of non-perturbative dynamics of, say, the hadron? So the picture that I argue emerges is that so if you think about some sort of initial profile of say field strengths in a proton, which is localized on this distance scale 1 over lambda QCD. So as you boost the proton relative, say, to an observer, the valence partons gets Lorentz contracted by a factor which is gamma. So their radius contracts. Okay, so they sort of start really sort of lying on a sort of a two-dimensional sheet. While the weak partons, they also Lorentz contract, but at a slower rate. Okay? And the question is, what is the scale that characterizes this dynamics? Okay, so even though you might think, say, at lower energies, these live all over, what I'm going to argue to you is that these get sort of Lorentz contracted as well, but at a different rate than which the valence partons Lorentz contract. You can also ask, well, what is the spatial distribution of these weak partons? So how do we see them localized? Say, if I look at a transverse cross section now, so if you have a probe that's seeing this sort of nucleus or proton come at you at very high energies, what is the distribution of these weak partons in the transverse plane of this? Okay? And so these kinds of distributions, that differential distributions that people are now talking about in perturbative QCD, are often called transverse momentum distributions, which give you the KT dependence of these weak partons, and so-called generalized parton distributions, which are the distribution and impact parameter, and trying to understand how these vary with rapidity. So you can think about actually doing experiments where you start to probe now within the structure of the weak parton cloud. So imagine you have a probe with some, so it's a virtual photon, say, which fluctuates into a quark-antiquark dipole. And this dipole has some size, say, r perp, which is the difference in the relative coordinates x perp and y perp, transverse coordinates. And they have some momentum fraction z, or 1 minus z of the energy of the virtual photon. Okay? And so this is scattering off. So you can alternatively rewrite this in terms of their impact parameter as such, and their transverse relative separation, which for a process like this turns out to be the relevant quantity. So here's the amplitude for, say, the exclusive production, say, of a heavy quark pair. So you have the virtual photon scatters to the proton. It produces this heavy quark pair, and then the proton remains intact. And this is a function then of the q squared for the process in momentum space, the resolution, and the momentum transfer, which is given by this capital K perp. And so this can be understood as a convolution of the wave function for the virtual photon to split into a QQ bar pair. And then for the QQ bar pair to sort of go into some additional final state, which is not specified here. Okay, so this is the overlap of the wave functions. And then there's this overall prefactor here. There's a phase factor, and this is then written in terms of convolution of the Fourier transform of the distribution impact parameter of the amplitude. And so this is sometimes called a dipole amplitude. And as I'll discuss further, this can be written in terms of correlator light-like Wilson lines. So this is kind of a space-time picture of our understanding weak partons. Much of the discussion in literature in the past was done in momentum space in terms of Feynman diagrams, while this is kind of more like a space-time picture in coordinate space in terms of these Wilson line structures. but as I mentioned, much of the early discussion was in momentum space. If you think about this in the language of perturbative QCD, how do we understand these weak partons? So think about, say, a generic process where you have, say, two gluons go to n gluons. So you have two hard gluons with, say, momentum PAPE, and so then they sort of produce sort of n of these soft gluons, and each of these has some transverse momentum and some x value, momentum fractions. Okay? And so, of course, when you go to n large, then a lot of these are V partons carrying small fractions of momentum photon. Now, as I alluded to earlier, when you go to very small x, so in this so-called Raju limit, okay, you get sort of the amplitudes can be described by the so-called leading logarithmic evolution in x, where you resum all such logs. So you assume that the transverse momenta are roughly the same, but there's strong ordering in x as you go to very small x. So logs in x dominate over logs in kt. So if you work in that approximation, then you can sort of resum all sort of these leading logarithmic contributions by taking into account all real and virtual contributions. So there's radialization of gluons that go on, and eventually you get a Pomeron solution where you can think about the amplitude as a compound color singlet object of radioized gluons. Okay? And so you can compute this, and if you ask, well, what is this amplitude that results? So this is now for in the forward limit of kt equal to 0. Then in momentum space, so this is the Fourier transform of the transverse size of the dipole, as I said, the relative transverse size. You find that if you solve the BFKL equation that corresponds to this, if you have some initial distribution which is peaked at some large kt, as you evolve in rapidity, or as you change x, you find that this distribution, as you boost, becomes broader and broader. And in fact, the solution really filters into the far infrared. So even though you start in perturbative QCD with the assumption that your transfer momenta are large, much larger than lambda QCD, you find that the solution doesn't respect that and actually diffuses into this region. So that kind of makes this kind of construction problematic. Now, you can also then go to next to leading log. So the state of the art is next to leading log, and there's already pieces of the next to leading log equation that's been constructed. So these are then summing alpha log to the n terms, and so on. That doesn't really change this basic fact. It kind of slows the diffusion into the infrared, but doesn't eliminate it. However, there's a piece of the physics that's missing when only one considers so-called ladder diagrams, where you just have, say, emission of gluons along the rungs of the ladder. So if you just had one ladder, that would be the BFKL Pomeron, where these two objects going down the ladder would be, say, radioized gluons, and there's some effective vortex leading to emission of gluons. Now, when you go to small x, it turns out that diagrams like these, where you can have, say, two such ladders, there's a ladder going to two such ladders. These are sometimes called fan diagrams. And this vortex is often called the triple Pomeron vortex, where so you think of one Pomeron merging into two other Pomerons. Such diagrams start to become important. Okay, so you can have diagrams where you have, say, two of these gluons, soft gluons, combined to find a harder gluon. Or you can have such kind of screening contributions. So these are actually these are actually cuts that correspond with different weights. And so naively, these kinds of contributions would be suppressed by powers of q squared times some infrared scale. But then as you go to small x, as you saw in one of my early slides, the gluon distribution grows very rapidly. Okay? So at some, as q squared gets smaller, the numerator becomes in the size of the denominator. And so all twist power corrections become equally important. Okay? And you can estimate when that happens. And that's when the occupancy is of this order here. And that turns out to be this is of order 1 over alpha x. Okay, so you can actually solve this equation self-consistently to determine what QS is a function of x. So this is some characteristic scale when the occupancy becomes very large and all such contributions become important. Now this remarkably, yeah, sorry. So QS is sort of an emergent scale when all of these higher twist contributions become of the same magnitude. I'll discuss this. That's the thrust of my talk is all about this scale here. So it's an emergent scale. It's a semi-hard scale, which grows as you go to smaller x. I'll come to that in a second. So I should mention that thinking about such divergences actually predates QCD. So there's a beautiful paper by Weinberg. So this is this classic paper on the soft photon and graviton theorem. And for those of you who are not familiar with it or who have not read it in a long time, I would really strongly urge rereading it. It's a very modern reading paper, well before QCD. And he talks about Yang-Mills theory and why Yang-Mills theory is problematic because of these massless gluons self-interacting. And he says that there's going to be all these very complicated infrared divergences. And to address this would be a Herculean task. It's also this nice quote by Wilczek, where he's really referring to the fact that this kind of perturbative Bremsstrahlung, which leads to growth in gluon distributions at small x, starts to be compensated by these recombination type effects, which actually have the opposite sign. And so there's a kind of Boltzmann type process where you have perturbative Bremsstrahlung producing more and more soft gluons, and then you have reverse processes of recombination, which sort of decrease the growth in the number of gluons, and that leads to some kind of steady state picture at some characteristic defined by some characteristic scale, and that's the saturation scale that I'm talking about. Okay, yeah. So of course alpha s in QCD only decreases sort of logarithmically with. But I'm really considering the sort of Raju limit where you really take s to infinity. And so in principle, I'm assuming a very small value of alpha s. So this is really, yeah. Yes, so QS is a function. I'll have a plot where I'll show you these you know, what that kind of looks like. But yeah, so the idea is that QS is a semi-hard scale, much larger in the Raju limit than lambda QCD. Sorry? Well, you can decide. I just wanted to set the stage. So if I fail, then you know, it's not quite Herculean. Yes. Yeah, a Herculean job requires a Herculean amount of time. And so it's like, you know, the Odyssey, right? So anyway, so if you think about, think about again this 2 to n process, and let's think about it in a very generic way. You say, what is the probability for, say, 2 gluons going to n gluons? So of course, it's some alpha s to the n. There's n factorial for the different combinatorics of the gluons. And then there's this, in principle, this degeneracy factor, which is e to the s, where s is the entropy of these microstates that comprise this blob that you produce, which comprises n gluons. Now, if you say that n is of order 1 over alpha s parametrically, then without this factor here, you'd find that such configurations, such classical configurations of high occupancy are highly suppressed. They will go as e to the minus 1 over alpha s. However, if s is of order 1 over alpha s, you see immediately, of course, that this can be order 1. Okay, so for very large values of s of order 1 over alpha s, you find that the probability for such a scattering is of order unity. Okay? And in fact, one can argue that this sort of classical lump of highly occupied gluon states saturates the Bekenstein area law in units of a Goldstone screening scale. which corresponds to the spontaneous breaking of concurrent invariants when you generate such large numbers of occupied states, as well as some global subgroup of SU3 cases, as I'll discuss. And so this is given by some screening scale, which is n times this saturation scale QS squared, which really corresponds to the maximal occupancy that one can generate. So essentially, so the statement is that the field strengths are so large when you produce such states that as you try and pack more and more gluons in some fixed region in impact parameter, there's a maximal occupancy that you can see. And that corresponds to the emergence of this scale QS. And so essentially the picture is that these weak partons at sufficiently high energies in the radial limit are completely color screened. And they live on a surface of a sphere of radius, which is given by 1 over k plus. This is the longitudinal momentum for the weak partons. Is on the order of 1 over k perp is on the order of the scale here. So this is the plot that I was mentioning to Cardi, that if you try to do this kind of a plot where you plot in the y-axis log of x or rapidity, which is the boost of the target with respect to the projectile probe, and then on the x-axis you have resolution scale. The claim is that for arbitrarily large q squared, there's always a value x at which the system becomes overoccupied. Can you saturate unitarity? Okay. So if you imagine a very small probe and you boost, to faster and faster speeds relative to you, you're going to see a very, very dense proliferation of gluons in this very small space. And that characteristic scale, which characterizes this line, is this QS of x. Okay. So for each value of q squared, there's an x, right, that gives you this maximal occupancy. Okay, so you can think about this as a unitarization boundary based on the argument that I just gave you, okay, where n times alpha s is of order 1. Okay. So how do we understand this phenomenon quantitatively? Okay, and ultimately interface with experiment, and where does the intrinsic non-perturbative dynamics that we all care about appear? Okay. But before I go there, let me just mention that this has also an analogy in gravity, and there's this really beautiful work by Lipata, which is actually almost completely forgotten. See, his original paper is from 1982, and this is a subsequent paper where he says that there's actually a double copy. So the original double copy that people now talk about quite a bit, in a somewhat different context, was due to Lipata, where he argued that the effective vertices in these 2 to n processes in gravity and in QCD have a structure such that the effective vertex, the Lipata vertex, is actually in gravity is a square of the QCD one. Okay? And processes such as radialization and so on happen very similarly, even though there's some qualitative differences. And so essentially, you can read this yourself. So essentially, he's saying you can construct a 2D effective theory, which describes all this physics. And then this work was developed into a very substantial program by Matti Ciappellini-Veneziano and collaborators, who sort of try to understand black hole formation in terms of gravitational shock wave collisions and so on. And in fact, one can use these double copy ideas, and this is something I'm actually actively working on and hope to report on sometime in the future, near future. But it's also amusing to realize that this kind of holographic description of weak partons that I gave you, where all the weak parton information is on the surface of this blob, was also prefigured in this very famous paper by Lenny Susskind, where everything's about weak partons and how these weak partons contract and so on on black holes. And in fact, he thanks Lipata. Now, all of these works, even though they discuss intensively small x and growth of weak partons, they don't really discuss explicitly this phenomenon of saturation. So can we understand this in a systematic way? And the framework which developed over the last 30 years. So this is work that I started here with Larry McLaren, and then developed for the next decades actually, substantially into an effective field theory, which is called the color glass condensate, aims to do precisely this. So again, if you think about this simple picture of a virtual photon that splits into some quark-antiquark pair that probes a target, which is kind of moving along here towards the probe. And so the target, if it is a very dense target, has large amounts of color, can sort of multiple scatter and emit radiation, soft radiation in interaction. And you find that there's an actual Born-Oppenheimer separation that emerges between the modes that of the target that on the order of the target, so momentum. So you have a very fast moving target with momentum p plus, and so if you look at modes in the order of k plus, and then the modes that are actually interacting with the probe, which have k plus much less than p plus, so they're sort of the result of all that Bremsstrahlung. And you see that the lifetime of weak partons is much less than that of the sources. Okay, so it's proportional x times p plus for a given k perp. And so the weak parton lifetime is very different. So there's a real separation in time scales between the dynamics of these longer-lived heavy modes on the light cone and these guys here, to the extent that you can really write down them as this kind of stochastic distribution of sources, which then couple in some gauge invariant way to the full QCD dynamics of the weak parton probe. Okay? So essentially, for each configuration row, and so because there's a large number of these sources, they live in a higher dimensional representation of the gauge group, and you can write down a stochastic weight for such a distribution. So each such row, you have a copy. So this is like a replica kind of picture where for each such row, you have this effective action for which you can then compute all the dynamics or whatever operators that you are interested in, and then average over all possible rows. So let me consider now a specific example where you look at, say, this onium production, as I mentioned, in the semi-inclusive process, where you have this classical field. So this is highly Lorentz contracted. Now, it turns out that for this effective action, there's a very nice classical solution, which corresponds to this solution of Yang-Mills equations in the presence of this iconal current, which is this stochastic distribution of large X sources at some given scale. Okay. And so you can find the solution. So Lorentz gauge turns out that just one non-zero component, so it's alpha. Okay. So this is kind of the non-abelian analog of a Coulomb field. Okay. So these are so-called Glauber gluons, as sometimes people call it, for reasons I don't understand. And so there's this non-trivial field, and this satisfies the Poisson equation. Okay. And so you can construct in this background, in the static shock wave background, you can compute propagators. So you can have a quark multiple scatter in this background. So that's interacting with this classical field. And these are represented by these path-ordered Wilson lines, okay, which are this rho over del perp squareds. And you can also have gluons and so on. And so coming back to this amplitude that I mentioned for exclusive production of QQ bar pairs, again, you have this convolution of wave functions, and then you have this object. The amplitude, you can write that as the sum of two terms, real and imaginary, from these light-like Wilson line correlators. And these are nothing but the color singlet C-even-Pomeron correlator, which includes all even powers of this color charge density of these color sources for a fixed configuration. And so, for example, if you were to project these QQ bar onto a Jape side, that's, you'll pick out this term here. While the imaginary part, right, these are all odd components in this expansion of these Wilson lines, and that's the C odd around correlator. Okay? And this would project, say, to an eta C charm meson. Okay? And for a simple picture of this stochastic weight for a large nucleus, which projects these two out, is just this kind of Gaussian correlator of these rows. So this is, say, the quadratic and cubic Casimirs, respectively. Okay? And so these will project out this Pomeron Audron. So it's a very simple picture just in QCD of the Pomeron and the Audron. Okay, you don't need any fancy mystification to understand that. And so you can now do evolution around this classical field configurations. So you can have all possible such gluons emitted. And the evolution equation that describes how these sources change with scale right, is this Bolitsky-Kovchegov equation. So for example, for the Pomeron correlator, it satisfies this RG equation with a kernel, which is this BFKL kernel. So this is the, and if I just were to ignore the second term here, that would be the BFKL equation. But now you have this additional nonlinear term. And this is a non-trivial IR fixed point. And that's what generates the QS scale that you see. So if you start with some initial distribution, right, this has a structure which then evolves away. And so you can think about the height of this initial distribution that evolves away as generating the saturation scale. And so this cures the infrared diffusion and transverse momentum. And you can have a similar nonlinearity for the order arm. That's a so-called BKP kernel, the Bartles-Grodzinski-Prashelowitz kernel. And so all this can be systematically recovered in this. So I'm running out of time. I just wanted to talk about the elephant in the room. And so you say, okay, you have this problem in the infrared, you cured it, and so on. Okay, what about confining dynamics? And the point is that it really never goes away. So even if you start looking at this evolution equation with some sharp input in impact parameter, where you really kill the impact parameter tails, with even one step in the evolution, you see that you recover this Coulomb tail, which then sort of grows very rapidly. Okay? In fact, when you look at large impact parameters, it grows exponentially in rapidity, while at smaller impact parameter, it really seems to obey this kind of saturation suppressed growth. And so the picture you can see emerging is that you have some kind of black disk, there's a parton regime, and then there's this whole sort of intrinsically non-perturbative physics of how pions go into, partons go into pions. Okay? In fact, there's a very beautiful, nice paper by Steve Gubser, which unfortunately is not as well known as it should be. And so where he finds a nice solution to this equation, where he takes into account the impact parameter. So if you think about the S matrix as a correlator of Wilson lines given by this, what he showed is that there's an underlying symmetry of the kernel, which allows you to write this S matrix in terms of some such object here, which is then which can be expressed in this way here, or equivalently, it has a geometric scaling property. The S matrix can be written as this QS times R, where this QS is then the maximum QS at zero impact parameter times 1 plus such a structure, Q squared B squared, where 1 over Q is inverse size of the hadron. Okay? So it's just a nice representation of these numerical results shown there. Of course, you still see that things sort of, the saturation scale gets to be small when you go to large impact parameters. And so I just want to say that, that you can actually now do experiments where you really start to probe this kind of distributions now. So this was the exclusive vector meson production that I talked about earlier for Jape size. And you can start doing experiments now, the IC, where you can try and extract the distribution of gluons as a function of impact parameter for different values of x, going all the way down to small x. Okay, and so you can do measurements of exclusive diffractive processes. And so hopefully this will start to really start to nail this down. So I'm really out of time. I think Alexa is looking very unhappy. I just want to mention a couple of other things. There's this very beautiful physics of color memory in the CGC, which I would love to talk to you more about, where it turns out that this is a deep connection of this classical solution to that of the memory effects that have been talked about. This BMS asymptotic symmetry is talked about in the language of in gravity, and the connections to soft theorems. And this is really a particular illustration which is realized in this framework, where you can map this transverse dynamics of the shock wave that I mentioned to you onto the celestial sphere at null infinity. And this QS kick that I'm talking about is precisely this color memory effect. Okay, and the Wilson lines are vortex operators in the celestial sphere. And the question is whether one can extract the 2D symmetries on this asymptotic celestial sphere to make progress in understanding this impact parameter physics. Finally, can we map this onto EFT for long strings? I know that we'll have a talk by Victor towards the end of the week, hopefully related to this. And the point I made earlier is that this is isomorphic to a heavy quark EFT. And so these closed loop dipole multiple Wilson line correlators are analogous to what's sometimes called potential in RQCD. The latter is well known how it's mapped to lattice into EFT for long strings. There are many experts in the audience. And can we do the same to address these parton confinement large impact parameters? And we need to find the right map. So this is actually a plot by Harvey Meyer and Mike Tepper. And they show that in gluodynamics, you can sort of extract these blue ball trajectories. And the question is, can we sort of construct something similar to understand parton dynamics at large? So I'm very sorry. So thank you very much for your attention.
Yeah, let's put a couple of relatively short questions before talking and snack. So, in Eric, and it's also very important about them, it's very in Israel. And it is about the separation is, I mean, conclusion was the separation doesn't disappear. So it disappears at temperature. So it's like end to end is, I mean, whatever that could be different. Two to end what you fundamentally threat. Maybe it's irrelevant to what you are saying, but
well, I mean, yeah. So I mean, of course, I was in Minnesota at that time, and that was a big topic of discussion and Holy Grail functions and so on, right? You remember this Holy Grail function? Or I think this is a qualitatively different phenomenon. I think because yeah, I don't see the analogy because here you're really creating this classical lump, and I think it's really the large entropy of this classical lump that we're yeah, right, yeah. Oh, there's a calculation. I mean, you can actually calculate explicitly that you get this Belinsky-Kopchakov equation is an explicit illustration of the saturation of probability. It's actually you get an infrared fixed point from first principles calculation. It's a generalization of the EFKL equation, and you can compute. So let me just complete my answer. There's also the computation of this to next to leading log and even beginning to next to leading log accuracy by Simon Carn-Huet and collaborators. So it's not just qualitative. Okay. Yeah. So I had to really skip a lot. And so what you actually get is a hierarchy of endpoint correlators. Okay. And that's called the Belinsky-Jimwilk hierarchy of equations. So you have 2-point correlators of Wilson lines, related to 4-point correlators, and so on. You have a whole hierarchy of multiple correlators. It turns out that in the large NC and large A limit, the expectation value of the product of traces factorizes in the product of expectation values, and you get a closed form expression. So this BK equation is very specific for large NC and also large A, which is the initial condition that you put in. But in general, you get a whole hierarchy of correlators. It turns out that because of physics is 2 plus 1D, you can rewrite this whole hierarchy as a Langevin equation in functional space, and you can solve it numerically. Okay, so you can compute all endpoint correlators numerically on a 2D lattice. Okay, and so that's kind of and you can look at the structure of quadrupole, sextupole, and those have quantitative experimental significance because they are accessed in various measurements at the LHC and future electron ion colliders. Yeah.
Yeah. We have another question.
Yeah.
So, it seems like you were suggesting commonality between the state of the large number of partons and some long string, like for black hole.
Yeah. So
know that the long string expands like square root of the log of
yeah, so actually, I mean, that's really where I want to go to. So there's, yeah, indeed. So you have a string in rapidity, right? And there's a diffusion of this in rapidity, right? So indeed, so there's a stringy picture that emerges. That's it. Yeah. I would think of it as a highly excited string. So, right, right.
No, there is a strange behavior which is
Gribov diffusion. You're right, right. That is what I'm talking about, actually. Yeah. Yeah. So I completely agree with you. In fact, what most of his discussion is really in terms of what we would call Gribov diffusion of the overall growth of the hadron, so to speak. Right. So indeed, that's not what I'm talking about, because that's not what I'm talking about, because my claim is that there's physics that comes in at intermediate scales, which is much smaller than that size. So the overall growth of the hadron is still there. It's not going to change because of the fact that you have the saturation at much shorter scales. And that's this tail and the impact parameter distribution that one sees, and that's the Gribov diffusion. So, but the claim is that the analogy to black hole physics is really this overpacking at fixed impact parameters that one sees, where you have highly occupied graviton states that you could interpret as such.
Right. So I think there's probably many other questions, but we should save them for the coffee break. We have about 45 minutes for that. And Raju, thank you again for a really exciting.
Sorry for